Tom, thank you for coming today to talk about this. This is particularly cool. We'll record the talk. There's about 20 people here right now. There's about another, I think we've got about another 80 or so in multiple time zones around the world, and they'll all get to watch this later on YouTube when I publish the talk. So over to you.
Yeah, great. So yeah, I'm happy to take questions from YouTube as well. If you share me the link when it's done, and I can keep an eye on that as things are, as people watch it after the fact. So thanks for the invite. It's nice to come and speak to you all about performance portability. So I'm Dr. Tom Deakin. I'm from the University of Bristol. And in this talk, I'm just really going to summarize some of the work we've done and what performance portability means to us, and how we might go about measuring it. And I'll show you some sort of case studies of where we've been doing that. So the first thing that I'll do is motivate why performance portability is important, and then I'll go on to define what it perhaps means. So if we look at the upcoming exascale and really pre-exascale machines, so in the HPC space, these are the next generation of massive supercomputers. And this is the selection of the ones that have made the most press of late. Most of them in the United States, but one in Japan at the top of the slide there as well. And what's striking about this is the diversity of different processes that we're going to be seeing in these big machines at each of the different installations. One of them is a homogeneous machine that from Deakin, the Fujitsu A64FX processor. The whole machine is made up of this single CPU. And in the US, they're taking a heterogeneous approach with CPUs and accelerated with a different number of GPUs, depending on the system. Sometimes they're 4, sometimes they're 6. But what's most striking about those is that in each of the systems, there's a different combination of CPU and GPU, often from different vendors. So we're seeing CPUs at this scale from ARM-based ones, such as the Fujitsu one, Intel and AMD, but also on the GPU side, GPUs from AMD, NVIDIA, and Intel as well. So if we have an application, an important science application, for instance, that we want to run at a very large scale on one of these machines, well, the chances are we're also going to need to be able to run it well on any of these other machines, or perhaps on all of these machines as well. So that means that code has to be portable between different types of architecture, different types of processor, and different vendors as well. We see this diversity move into the cloud space as well. So this is just a quick survey that I looked at AWS, and as of course in this hackathon you've been using lots of these processors already. There's obviously the Graviton 2, the ARM-based processors from Amazon, but they also have offerings from Intel and AMD, and the same is true in the Oracle Cloud with the Ampere Ultra CPUs there as well. Those are 80-core ARM-based processors as well. Plus, of course, they have all the GPU offerings, plus whatever specialized accelerators that they'll offer as well. So we're seeing the need for applications to be portable between a huge variety of different architectures and different processes. And because we care about performance, if we are talking about a high performance code, a HPC code, then we want to get good performance on each of these different processes too. It's worth just looking at what really is materially different between these different types of architectures. And this is why I like to show this little slide that sort of compares some of the key features of perhaps CPUs and GPUs. So with CPUs, typically and traditionally, they have some number of complex cores. Now those complex cores have got lots of resources. They can do very clever things with the instruction stream, things like branch predictors and big wide out of order resources. Previously, I suppose a few years ago, there was a few complex cores, and now we're seeing that we're really in the many core era where the Graviton 2, 64 cores per socket, and the Ampere Ultra with 80 cores per socket. That's a good number of cores. If you compare that to GPUs, they've typically had lots of lightweight cores, so much more simple cores that are specialized to do a particular operation and rely on other parts of the device and the programming models and things to do a lot of the of those things like scheduling of instructions, that sort of thing. It's not necessarily all built into the hardware. And then if we look at maybe what else those cores can support, well, CPUs have got, vector SIMD units that are becoming wider. So on the Intel and x86 side, AVX512, and on the ARM side with SVE from between 128 to 2048 bits. This has obviously been increasing up to about, this 512, and the Fujitsu processor that we're seeing has got SVE 512. On the GPU side, this vector unit is even bigger in a very real sense. If you look at NVIDIA GPUs and you start talking about warps, they behave in a very similar way to SIMD units might in a CPU. And those are 32 wide. You can do 32-bit floating point operations in a SIMD way, which is much larger still than on the CPUs. But we're seeing the cores in GPUs becoming much more complex. So those things that have been in CPUs, such as specialized accelerators for particular domains like cryptography or even SIMD in some sense, we're seeing similar things coming to GPU. So things like specialized in-core accelerators, things that can do like tensor products and matrix multiplications. And we're seeing that creep into CPUs with some extensions from some vendors as well. On a manufacturing level, we're seeing CPUs are starting to take on board this chiplet idea, where your whole processor socket is formed not just of one piece of silicon, but multiple pieces of silicon all packaged up together. And that hasn't quite spread into the GPUs. They still make one large chip in the GPUs that are available today. What that chiplet does, and it's useful for us as application developers to know about it, is it does encourage these non-uniform memory access between the different chiplets. There's a different memory access timings that we might need to take into account. GPUs have typically always used the latest memory technology for its main memory, things like HBM and before that GDDR. And while CPUs are still mainly DRAM, we're seeing that they are adopting these newer memory technologies as well. So the Fujitsu ARM A64FX is HBM2, and the recently announced NVIDIA Grace is using mobile LPDDR5X, so different type of memory that's going to be built onto CPUs as well. And in both cases, this cache hierarchy is deep. There's multiple levels of cache there. We have some idea of distance between different parts of memory, depending on what we're trying to access. So really, although they look very different and we have to think about programming them in a different way, with CPUs, we can program them using our parallel programming model. With GPUs, we often have to think of this split memory space and some idea of offloading to a GPU. But actually, as a processor, they both fall on this spectrum of being optimized for a particular type of workload. And CPUs have traditionally been on this latency optimized. They're designed to access memory, keep it close in the cache, and do lots of instructions in a latency optimized way. And GPUs are on the other end of that spectrum, where they have much wider parallelism, much more cores, and can do much more work all at the same time. So this more idea of throughput optimized. So really, my point of this slide is just to show that all these different processes all kind of fall somewhere on this spectrum of being optimized for latency or throughput. And as an application, we want to try and take advantage of whatever processor we can and achieve the best performance we can given how that processor has been optimized. So this leads on to what is performance portability. And I like to show this picture on the bottom because it really can mean something different to different people. And it also depends on your perspective and perhaps what is quite a subjective question to ask. And really it almost depends in some ways on what kind of performance you're willing to tolerate based on the particular situation that you're running your application in. So a definition that we like to take is this one in the box there. We say that a code is performance portable if it can achieve a similar fraction of peak hardware performance on a range of different target architectures. So what does this mean? It means that we can have our application, our code, we can build it on a wide range of different architectures that we care about. And hopefully that range of architectures is quite broad. We're able to run it on different processors from different vendors and incorporate new technologies as they come downstream as well. And then on the performance side, it means that we're hopefully going to get a good fraction of the peak performance that's possible on each of those architectures too. So as a number in the air, we might hope to say, well, we're going to get 80% of the peak performance on all the hardware that we're going to target. And that's an ambitious goal, but it's something that we try and strive for. Part of the picture of performance portability is choosing a programming model that enables you to get a performance portable code. What this really means is there's kind of two ways you can think about this. The first is using standard languages, things like C, C++, Fortran, those sorts of things, and also open standard parallel programming models, things like SYCL, OpenCL, and OpenMP. These are vendor neutral, and many vendors contribute and support these different programming models, and they're all built up in some sort of IP framework where vendors can actually have a big discussion about how that programming model should be developed in the future. This means that we can kind of, it's a safe bet. We know these programming models are going to last a long time. So we're going to invest in those in our application and write in a way that is performance portable, using something that enables us to write such a performance portable application. Now, the other side of this is we perhaps try and abstract away over the vendor specific parallel programming models. And we might use an open source programming abstraction, something like Cocos or Raja. And in this category, I also include domain-specific languages and the compiler that you must implement with your DSL, your domain-specific language, in order to support that. So a compiler is quite a grand term for that, but really it's the mechanism that converts the code you write in the DSL to whatever it is underneath that gets run. So maybe it's just a source-to-source translation. That's what I'm calling a compiler in this sense. So all of these approaches enable, as an application developer, us to write an application that can then at least be portable in the first instance. It has to run on multiple different platforms. And then also express our parallelism, express our code in a way that enables those languages and models and abstractions to get the best out of those patterns and express them well for each of the hardware that we're targeting. So picking something that's open and open source and open standard is the first step to enable performance portability. And part of that, of course, is just through portability to start with. So as a little case study of some of the things that we've been doing with performance portability, I'd like to share with you this small code that I wrote called Babelstream. It's basically a small benchmark that measures memory bandwidth for a number of kernels. It's based on McAlpin Stream, which is a fairly common benchmark that we see in HPC, but it's written in a modern programming style where the arrays are allocated on the heap. So we call alloc so that we know how we can malloc call, so we know at only at runtime how much memory we're going to have. And also the problem size is known as a command line argument. We only know what the problem size is when we actually run. So the problem size is the size of the array. This is different to McAlpin Stream, which the problem size is known at compile time. The arrays are on the stack. So a compiler can do very smart things and do a lot of optimizations with that extra knowledge it has about how big the memory actually is. But for a real science code, of course, we read in an input file, we have different benchmarks. And in this hackathon, you've been creating lots of different benchmarks, and they're probably all in input files that you read in from your binary. You're not actually baking those into the binary themselves. We also write this in lots of those different programming models just to explore the space, really, and to see what they can do and what sort of performance portability they might offer. And all the kernels look like simple vector operations. So the one I'm going to show results for, called Triad, just scales one array, adds it to another, and stores the result in a third. It's an open source benchmark, and you can check out the code at that link there. So in order to measure performance portability, you have to have some sort of platform agnostic way of measuring your performance. Sometimes you want to just compare the runtime of an application on different processors. And that's a useful kind of comparison to figure out maybe what platform works best for my application. Which one am I going to invest in the most in order to get the most science done, the most throughput for the application, which is fastest. I'm going to use that one. But of course, that may not always be available. and you may have to run your application elsewhere. And you also want to make sure that you're running your application well everywhere. So you need some way of measuring efficiency, mainly because those processes have different performance characteristics. So as part of the performance portability kind of methodology, there's two efficiencies that some folks at Intel came up with. The first is architectural and the second is application. So architectural efficiency, and I'll show you those for Babel Stream, it's the percentage of the peak hardware performance that you're achieving. So you might measure or model with some basic performance model what memory bandwidth in gigabytes per second that your application achieves relative to the peak hardware, or the same for flops, floating point operations per second. And this is always compared to whatever the theoretical maximum that processor can do. So you do a quick internet search and you find the technical sheet and you can work out what those numbers are. You measure those in your application and you compute a percentage, and that's your architectural efficiency. Now, for some applications, that's not very tractable, and you need to take some sort of other measure. So what the application efficiency is from a situation where you might have a very specialized hand-tuned unportable best version. Say you decided to write your entire application in assembly, and that only works on the one particular processor. That's probably the fastest thing that exists. But then you have a new processor to run on. You rewrite your application in some performance portable programming model, and you then can compare on that platform to that fastest. It's kind of like a world record, but not necessarily maintained anywhere. So you're comparing to the best known performance that you've ever seen for that benchmark running on that application on that particular piece of hardware. So in that way, the architectural efficiency would never see 100% architectural efficiency, but we might see 100% application efficiency. This is where the results come in. So this is for Babel Stream. And in this, I've got 6 different parallel programming models that you can see on the bottom of these 2 figures. And down the left-hand side, up the sort of y-axis, if you will, I've got 15 or so different platforms. And on, if I just annotate them, you can see the range of different types of CPUs and GPUs that we're running on. This is quite a broad sweep through all the different processors from most of the major vendors, including the ARM processors, the Graviton 2 that you've all been running on in this hackathon as well. The left-hand heat map here shows the peak performance of the benchmark. So this is the raw output. It measures memory bandwidth. So yellow is the higher and purple is the lower. And each of the processors is measuring, for each of the processors, we measure what gigabytes per second we achieve. So this figure is useful for finding out what's the fastest device in this, in terms of main memory bandwidth, memory throughput of this particular set of processors. We can use that on the left. And we see that those processors that use high bandwidth memory beat those processors that use, say, DDR or something, which inherently has much lower memory bandwidth. So that's one comparison. On the right-hand side, we start to unpack this idea of performance portability a little bit more. We know that Babel Stream Triad is memory bandwidth bound. So what percentage of that peak memory bandwidth that's possible on the different processor do we actually achieve? And this is what I calculate on the right-hand side in this figure here. And you can see that in lots of cases, we're seeing quite high performance for each of the processors. And many of the models let us get close to 80% or above of the peak performance on all of the different platforms, which is great, or most of the different platforms at least. So this is quite a lot of data, and maybe our platform set will be smaller, and maybe we won't be looking at quite so many different applications or programming models. So we came up with this Cascade Plot, and the reference there is some more information about how to construct these. To make these plots, what we do is we compute the application efficiency first. So I converted from architectural efficiency to application efficiency. And then for each of the programming models or applications, I sorted those efficiencies. So I use an Excel spreadsheet or a Jupyter notebook, which I've got a link to on the next slide. I can sort those application efficiencies. And I plot those with the solid lines on this figure here. At the bottom in this sort of color bar, this is where I recover that different ordering, because for each of the different applications, then my list of platforms is going to be in a different order. What this figure enables us to do then is start to unpick where the performance portability starts to suffer. Where do things go wrong? is there a trend in that color bar at the bottom where things start going wrong and start struggling? So for instance, that bottom line there on the color bar for the orange program model, that's CUDA. That's a benchmark in CUDA. As of today, CUDA only runs on NVIDIA GPUs. So we see that on 4 GPUs, we had 4 NVIDIA GPUs, then CUDA runs, but after that, it stops running. It's not supported on any of those different CPUs or any other GPUs. So we can perhaps identify that as a particular trend. Same if we look at OpenACC above, it runs very well on 4 of the GPUs. And then when we start adding on CPUs, the performance starts to tail off, but it is still running. We're still being able to run our code. It's portable, but the performance we're seeing suffer. And we see this in 2 ways. We see the line graph start falling from the top to the bottom, and we also can start identifying what type of trends and what devices what classes of devices they might be corresponding to in the color bar. If we take the top line of the color bar, this is OpenMP. OpenMP supports CPUs and GPUs, and we see it runs very well with very close to peak efficiency on CPUs. But as we add more and more GPUs and perhaps some CPUs, we see the efficiency drop a little bit, but that's the kind of trend that we're picking up. By plotting everything on one graph like this as well, with these different kind of cascades as they cascade down from the top left over to the right-hand side, we get this intuitive idea of an application is more performance portable if it can reach further along the x-axis. It's more portable by doing so, and by keeping its height, by keeping higher up on the y-axis, it achieves more performance over more platforms, so it's more performance portable. So really we're aiming for this idealized top right hand corner in this figure, and being able to compare different types of applications in this way is very useful. So of course, if you have more than one application or more than one kernel that you care about in one application, you can plot each of those as a line where you replace the programming model with lots of different applications, and this technique will still work and be useful. So if you're interested in plotting these types of graphs and calculating the performance portability metrics and efficiencies and things, then we have a Jupyter notebook that helps you do all of these things, and there's a link at the top for you to go and investigate those. Please try these things out and let us know if you get stuck with the script. So we're more than happy to help fix those bugs and fix any issues that you raise. So the next slide, which has a big white square on, so I will just try and find out where that's coming from. Bear with me. There we go. Back to Zoom. There we are. Not sure where that came from. So this is a figure taken from a recent prize-winning paper from ISC, from other members of the HPC team in Bristol, from Andre, Tom, and Simon. And here they looked, instead of a memory bandwidth bound application, a compute bound application. This code is called Minibute. It's a molecular docking code, and this is a mini app that strips away some of the complexities. Essentially, it's used for drug docking, and it takes candidate molecules and the different proteins and tries to make them sit together nicely in all sorts of different poses until one of them docks in a particular efficient way that can then be used to help maybe treat a particular disease or something like that. So compute bound is somewhat more interesting. It's much more dependent on the compiler optimizations and the way that the instructions are scheduled and the type of code and what instructions are selected than it is for a memory bandwidth bound code. So it's a very interesting test case. And for here, again, they looked at different programming models, and they've got a number of different platforms. There's much more detail in the papers and the presentation that they gave at ISC, so I would go and check that out as well. But firstly, we can see that in general that there's a good performance on a number of the processors as well. We're nearly 60% of peak performance on Cascade Lake and Rome. And that, again, there's ways of implementing and choices that you make in how you've implemented your code that enable you to get close to that best performance across all the architectures in the platform set that you are interested in. Of course, with other models where there is performance improvements to be made, this is useful information to try and help ensure that those things improve in the future. So do check out that paper if you are interested in some of the approaches they've taken there as well. Another part of performance portability is this idea of productivity. So we have this idealistic application. So we have one version, it's performant, it's portable, and we can be productive with using it and writing it. In general, what we might expect is if you start significantly specializing for performance or for portability, that can particularly impact your productivity. For instance, I need to go and rewrite my code in assembly. That's really going to impact my productivity and impact my portability too, but my performance might go up. So understanding how things move around this landscape is really important. Intel made a tool called the Intel Codebase Investigator. It helps you measure the code divergence, so where you might have specialized your code using a CPU processor. And we can combine that with this idea of the performance portability. So here on the left hand, the y-axis is an average of my efficiencies, just the harmonic mean of the efficiencies I've measured. And we can produce this figure that compares my sort of average performance portability with how diverse and how much my code diverges or how similar it is to each other. And by plotting a journey of an application as it starts to be optimized or specialized or abstracted, as we added abstractions to help maybe hide away some of those optimizations we have to make, and those specializations, for instance, we can start to track how it moves around this figure. And this is something that we're looking into at the moment. And it's certainly very interesting as we look at the codes that you've all been optimizing in this hackathon. It would be interesting to see how they've progressed and what their performance has done in a similar kind of way as you've started to optimize the applications. So this is coming up in a paper in an IEEE SciSe magazine article coming up soon, so do watch out for that when that arrives. So I'd like to finish with some sort of practical tips about performance portability and kind of best advice from all the experience that we've built up in Bristol studying this for a number of years. The first is to measure and track your performance and your portability. So build your application on multiple platforms, make sure it builds with multiple compilers. That's really important for portability. Make sure that it works on lots of different processors, lots of different operating systems, lots of different environments that you may need to run your application in. So that's part of it. Make sure you've got good code hygiene, make sure it's a portable code, and then actually run your code on all those different platforms and measure the performance and hopefully track it in some way over time as your code base changes. As I said before, use open standards. These are a way that you can guarantee that you can express your parallel codes in a way that's going to be lasting and well supported by lots of different vendors. That's part of the portability picture as well. And then at an application level, exposing the maximum concurrency and parallelism at all levels of your application is really important. Some different processes are going to have different amounts of parallelism that you need to exploit from the application level. So when there's a small amount of parallelism in the processor, it may be easy for you to find that in your application. But when you have highly parallel processors, as they are becoming more and more parallel, you need to find that concurrency in the application and make it available to be taken advantage of by those processors. Then optimize for this diverse processor landscape. So as you, it kind of ties in with the first point about measuring and tracking your performance on a range of different processors. So measure your performance on your different processors, optimize your code on one, but also optimize it at the same time on the other, and make sure that any optimizations you're introducing for one platform only help or don't negatively affect any of your other platforms. So you can avoid over optimizing for one platform, which is going to hurt this performance portability. Part of this might be building in paths for specialization and auto tuning. So specialization could be as simple as you have a matrix multiplication routine and you need to call a specialized DGM library, the matrix multiply library, from the particular processor vendor of your choice. That's a path to specialization, making a library call. So you haven't written it yourself. You've built in a path to specialize using an optimized library. And also things like auto tuning. The Bude Mini app is something that is very useful. There's a way to tune the number of poses you might try in a block before you go around the next iteration of the loop. And you might want to tune that size based on the architecture, based on how wide the vectors are, how big the caches are, all those sorts of things. So build in these parameters that you can choose and tune, perhaps with some auto tuning framework, to get yourself the good performance, and in a way that your application becomes portable by selecting a good range of these parameters. Now, I know there was some work done at Bristol with a colleague who's now left a few years ago, James Price. He looked at this multi-objective auto tuning. So he was doing some auto tuning techniques across multiple processors all at the same time to find a common set of those parameters that ran well everywhere. So if you're interested in that and all the other work on performance portability, do have a look at the group's webpage, which is at the bottom of that slide there. So with that is everything from me. I'm happy to take a few questions from those on the call if there's time, but do comment in YouTube or in the Slack that I think is being supported, and I'm happy to keep an eye on that and answer questions over the next day or so. So thank you very much. Any questions?
Thank you so much, Tom. That was absolutely fantastic, and I think really useful for the students, I hope. I think it's always a bit daunting when you're given a fairly new application and a couple of different bits of hardware, and trying to understand, well, what's good. So having some concrete metrics coming out of things like this is so useful.
I agree. I think if you've helped people work out how to reduce the space for optimizing, because it, like Ollie says, is daunting. Mm-hmm. And the assumption can be we must maximize everything all at once. I think John said a similar thing yesterday when he was talking about profiling. Don't go and improve every single thing that you know about at once, because you may lose a whole lot of performance from one thing that you did that was crap. That's really good.
Yeah, and one of the questions that we had coming from the students, I think probably yesterday or even the day before, was when do I know when a good time to stop optimizing an app is and move on to the next task? And we kind of joked about that at the time, because it's such a difficult question to answer, because you never know what the trapped performance in there is, especially when you're talking algorithmically. But to actually concretize some metrics to say, hey, you're getting near the maximum that you can on this hardware, unless you are doing something to change the algorithm, it's probably not worth doing anything more. And that's why I think kind of things like roofline models and everything like that were so heavily adopted by the community, because you know what, it's really nice to plot on a graph. Yeah, I'm getting 90% of what I would expect to be able to get. I'll call that done. Because that last percent. Sorry, go on.
Yeah, a roofline model is really useful for a kind of an initial port of call. I know the Intel profilers give you one with them. I guess, how is the progress with the ARM tool chain? Do they do similar metrics and things?
We have one up on GitLab that does it.
Great. So there's a tool that all these people can, on the hackathon, that you can go and try out. That's fantastic. Yeah, it's really useful for giving you that. What am I likely to be bound by? Compute or memory traffic, and then if it's memory traffic, which level of the memory hierarchy might I be bound by? The one thing to remember with roofline, of course, is that those that are empirically those that are generated by measurements, it measures the actual amount of memory movement and flops that you do. So you have to take in mind, well, maybe I'm doing a whole load of extra compute that I don't need to do, which is going to skew where it might live on the graph. So you have to have a look at the code and think, does this look reasonable? Does this look like an optimal implementation? That you have to bear in mind as well. Thinking in a perhaps more analytical performance model way, and combine that with the knowledge you get from a roofline. All these are kind of data points that you can use to help kind of understand where you might fit. And as you said, it is this journey. You don't need to do everything all at once. Start somewhere, measure it and plot it somehow, then incorporate new platforms, new compilers and new parts, and then see how you go. Try out an optimization, see what happens. It might work, it might not work. And it's kind of creative and playful, really, but just tracking your journey as you do this, I think is really important.
I can't agree with that anymore. I think the more you try out different hardware, the more you learn about different applications and the nuances of them, and taking that experience back to other bits of hardware kind of really helps you on this journey. I mean, I won't go into it in too much detail, but for me, one of the kind of best things about things like KNL was forcing you to learn new things about your applications and the parallelism and the limits and its memory usage that just weren't a factor on other hardware. And so,
as it turned out, it also forced you to learn things about Xeon, which made your code better.
Sure, and that was the point. You optimized for KNL and then took your code back to Xeon, and
it worked
found
better.
you got most of those benefits on Xeon as well. And even Intel were honest and say that's not a flaw. That's a win. Faster code is faster code. So yeah, the more you try new hardware and the more you try new compilers and compiler flags, the more you learn.